Hi, it's Romeo Bruni again, and today we're going to talk about binary stars. Binary stars are very important because the majority of stars in the universe are binary stars. In fact, approximately 50% of the stars, when you look up in the night sky and you see a star, you may only see one star, but actually 50% of the time those stars are binary. The percentage of binaries is going to vary depending on the type of star. For very massive stars, it's actually quite high. 70–80% of massive stars are in binary systems. For stars like our sun, approximately 50% of them are in binary systems. For lower mass stars like red dwarfs, down to 20–30%. But overall, we can say about 50%. Binaries are very important because they give us a lot of information that we wouldn't otherwise have. And since such a plethora of stars are binaries, that alone is reason to study them. But let's look at them in a little bit of detail. Binary stars can be divided into various types. One of the most important types and obvious types are visual binaries. Visual binaries are when there's two visible stars actually in orbit around each other. This needs to be separated from apparent visual stars, which are two stars which just look close together in the night sky, just because they're lined up as such, but they're not actually close together. They're separated by great distances. But if two stars line up in the sky, they may actually be near each other, in which case they are orbiting in a binary. Of course, binary stars, when we talk about stars in orbit, any type of stars can orbit around each other. And since we've discussed in a previous YouTube video that you might want to look up on the types of stars, there's four basic types of stars. Protostars are baby stars, not yet formed. Main sequence stars are the majority of stars in the sky, since you spend approximately 85–90% of a star's life is in the main sequence. The main sequence stars are all it's a mass sequence as shown on the Hirschsprung-Russell diagram, with the greater the mass, the greater the luminosity. The dying stars are stars that have now gone off the main sequence, are no longer burning hydrogen to helium at the core, and they begin to fluctuate and pulsate and grow in size, and they'll often grow to either red giant like our sun will, or massive stars will go to a super red or super blue, blue supergiants. And of course, dead stars. There's three types of dead stars: white dwarfs, neutron stars, and black holes. Any combination of these stars can form into a binary. Obviously, protostars, since they're baby stars, might form into a binary right from the start. But since the stars in any binary pair will evolve so that initially they're both going to be main sequence stars, that will be your visual binaries. And then later, one of the stars may be in the act of dying, a dying star, or be a dead star, in which case the nature of the binary is obviously going to change. So we've discussed visual binary, which are basically when two stars that are quite visible, which are either a main sequence star or a dying star, are in orbit around each other. For example, as we showed with the Capella binary system here. Another very, very important category of binary are the spectrographic binaries. In spectrographic binaries, the two stars that are in the system are so far away that they cannot be distinguished using normal telescopes or interferometry methods. So they're really distant, and the light coming from them appears as one light. But if you analyze that light and do a spectrograph of that light will actually divide into what's obvious two light patterns. Because there's two stars, and they're going to be different masses and temperatures, so they're each going to give off a different light spectrograph. And not only that, so just by looking at the light and saying, hey, wait, this is breaking down into two spectrographic light types and not one, you know right away there's two stars. And not only that, as you can see, the stars are in orbit around each other, so at some point, depending on the alignment, one star will be moving towards you, the observer, and the other star away, and vice versa. So the spectrographic color coming from each separate star is going to vary from Doppler shift. Again, the Doppler shift is whenever any wave is coming towards you, the wavelength is shortened and it shifts towards the blue. If it's light, if it's sound, you get the classic shift of the vehicle passing you, where it's quickly and higher pitched wave come towards you, as it passes. So the same with visual light. The light that's coming, when the star's coming towards us, it'll be blue shifted, and away from us, it'll be red shifted. So you actually look at the spectrographs and see not only that they're two different spectrographs, but you can see that one is moving away and then shifts around and is coming towards, and so on. And you can obviously figure out the period of the orbit by measuring the waves, the frequency of the light as it comes to you. So those are spectrographic binaries. Eclipsing binaries are even more helpful than spectrographic binaries, because not only do you get the spectrographic data, but in an eclipsing binary, you have two stars orbiting in each other such that the orbit of the two stars is aligned such that one eclipses the other. And if two stars, if one star is much brighter than the other, when it gets eclipsed, you get a major dip. When it reverses around and the less bright star gets eclipsed, you get a dip also, but less of a dip. But you'll be getting a regular series of brightening and lessening of the light as they eclipse. This is very helpful because when you get eclipsing binaries, like this, it's very easy to determine the period of their orbits. And once we get information concerning the length of the axes of their orbit, you can figure out the mass from knowing the period and the radius of the orbits. So those are eclipsing binaries. X-ray binaries. X-ray binaries, I love X-ray binaries. X-ray binaries are very important. In an X-ray binary, you have one star that's usually perhaps large and dying, and you have the other star is either a black hole or a neutron star. And what happens is that the other star, because it's starting to die perhaps and expanding, it starts to lose its matter via an accretion disk into the other star, into the other neutron star or black hole. So matter is being fed via Lagrangian point 1 into the other star. As the matter accretes around the other star, which is a black hole or a neutron star in this case, it heats up, it heats up, it heats up, it gets hotter and hotter, and as it gets hotter and hotter, it starts to emit light. So even though it's a black hole doesn't emit light, but the accretion disk emits a lot of light. Light up to including X-ray light, and we can see that X-ray light from the accretion disk. And not only that, because the black hole is spinning and magnetized, you get the spinning matter going in, you get jets being emitted out from both ends. And so this is an example of this type of binary system where you have a huge star here feeding matter into a black hole via an accretion disk. So in this case, because it's a high mass partner to the black hole binary or neutron star binary, the big star itself is also going to be emitting a lot of light, including up to X-ray radiation. And matter being fed into the accretion disk is going to start to heat up and emit a lot of radiation, including high energy. And indeed, you also get the radio jets, which are relativistic matter being shot out because of the magnetic forces involved. And when ionized matter is shot out at relativistic speed and it's in a swirling pattern, so it's being accelerated perpendicular to its motion, that releases what's called synchrotron radiation, which tends to be in the radio wave band. So these X-ray binaries are going to be emitting not only X-rays, but if they have the jets, they're also going to be emitting radio waves. Of course, in a partner like this, the partner does not necessarily have to be a high volume big star. It can be something small like a white dwarf, in which case the white dwarf will be not bright in itself. It'll be small. So you'll have a small star here, which in it itself, because it's small, won't be emitting a lot of light. But because it's feeding matter into the other partner, the accretion disk around the black hole / neutron star will again start to emit X-ray beams. And of course, you'll get the jets shooting out in either direction from that black hole. So it too will be an X-ray binary. Those are called low mass X-ray binaries. You're going to be getting the light basically from the accretion disk of the black hole, as opposed to a high mass X-ray binary where you're going to have both stars contributing to the light being emitted. So those are X-ray binaries. Also very important, supernovas and nebulas. Now I mentioned this under binary systems because a certain type of supernova, a supernova type, oh, I put 2 there, but that's wrong. It's type 1a. Type 1a supernova. In a type 1a supernova, basically you have this situation. You have a white dwarf, and you have a neighboring star, which perhaps because it's dying is swollen up. And white dwarfs, as we know, according to Chandrasekhar, maximum weight of a white dwarf can be 1.4 solar masses. So all white dwarfs in the universe are under 1.4 solar masses, and they are held up by what's called electron degeneracy pressure. They're the remnants of a dying star. Any star under 8 solar masses will eventually die, slough off its outer layers, and condense down to a white dwarf, which isn't as heavy or dense as a neutron star, or obviously a black hole, but is still super, super dense. And the maximum size, or what mass it can be, is 1.4 solar masses. So if you have if you have a white dwarf, say at 1.3 solar masses, and it's in a binary system where the other star starts to swell up, so it starts to feed matter in to the white dwarf, again via an accretion disk, such that the mass of the white dwarf increases 1.3, 1.4, sorry, 1.3, 1.35, 1.36. As soon as it hits 1.4 solar masses, it can no longer support itself from weight, and gravity wins out, and you get a sudden core collapse, which causes a rebound, which causes the whole thing to thermodynamically, thermonuclearly explode. And the total mass of that white dwarf, 1.4 solar masses, in fact, we know the exact mass, gets exploded out into space in an expanding ring of iron and nickel, which is formed in that last explosion. And because all the energy is transmitted or converted into, all the matter is converted into this energy system that expands, we know exactly how much energy a type 1a supernova is going to put out. Therefore, it is one of the most important standard candles in the universe, because from a spectrographic analysis of any supernova, we can determine if it's a type 1a. And if we've determined it's a type 1a, we know that exact amount of energy that type 1a is going to release when it explodes. And since we know exactly how much energy is released, and we compare that to its apparent brightness, meaning how much light we actually see coming from it, then that tells us exactly how far away that star is, that exploding star. And since they happen to be in galaxies far, far away, then we'll know exactly how far away that galaxy is. And measuring distances in astronomy is one of the most difficult things. So type 1A supernova is so important. So here we see a type 1A where we have a bigger star feeding mass into a white dwarf, and it keeps feeding it, and slowly the mass increases. As soon as it hits 1.4 solar masses, it like totally explodes, and all the energy matter gets sent out into space in an incredible shock wave. If the amount of matter that goes in isn't enough to go over the Chandrasekhar limit, but it still gets super hot, it can also undergo thermonuclear explosion and get shed out into space in what we call a nova. So a nova is kind of like a baby supernova 1A, where you get some of the stuff that's converted into pure energy and iron, nickel, and sent out into space, but not all of it. So a remnant white dwarf will still remain after a nova, but not after a supernova. Very interesting, another type of binary system is when you have two stars that are perhaps dying. And dying stars pulsate and they grow and they send off a lot of solar wind. And when two dying stars are in orbit around each other and they're each giving off a lot of solar wind, the solar winds can collide when they come close in their orbit. And the collision of the solar winds will actually create like a dust. And that's exactly what James Webb photographed in this star system, where we have a very large O-type star circulating, or sort of orbiting around another very, very large star. I think it's a Wolf-Rayet star, which are super big stars. And thus, because they're both dying and giving off a lot of solar wind, the solar winds are going to collide every time they get close in orbit. So every collision is like the ring of a tree. Every collision denotes one orbit where it's come close to each other, and the solar winds collide and you get a ring. So it's like the rings of a tree. Instead of years, it's denoting how many orbits. Of course, another type of binary system is what we call an astrometric binary. In an astrometric binary, we have a star, a visual star, a star you can see, and it's orbiting either a black hole or a neutron star. Now, in this case, they're separated by distance such that matter is not being accreted to the black hole or neutron star, so it's dark, it's black. But yet, we see this star, even though it's orbiting a black neighbor, an object that emits no light, we see it moving back and forth, because even though it's the object it's orbiting around isn't emitting light, it's got the gravity. And so the gravity is there, and you have the other star going around it and being jerked around, as, you know, because it's being pulled on by the other star. And this type of star, this is one of the first ways that we discovered black holes, because we found stuff orbiting around them when there was nothing there, yet massive stars orbit around them. This is especially true at the center of our Milky Way, for example, where Sagittarius A star, or the supermassive black hole at the center of our galaxy, has massive stars just whipping around it, and you can actually see them in a video clip, an actual video clip that they've taken with time lapse and put together, that won a Nobel Prize, showing massive stars whipping around empty space. That would be a type of astrometric binary, if you will. So, in summary, binary stars are very important. The majority of stars in the universe are in binary systems. And because of that, the two stars influence each other. And therefore, you need to know about binaries if you want to study stars, because of the dramatic influences between the two stars in binary systems. the influences between them are so great that if you didn't understand binaries, you wouldn't understand what you're seeing. My name is Romeo Bruni, and I hope you enjoyed this.